So now we're gonna learn about how to make this network intelligent. You know, like how can it recognize the digits? So going back to the baby example, now the baby says something when we show it a picture. Let's say revisiting a new. Let's take a new example. We show the baby a picture of a 1. The baby goes, "That's a 5." We're gonna be like, "No, you silly goose, that's a 1." Okay, that's how we teach a baby, and something in the baby's head is gonna click, and the baby's gonna start associating like that image of a 1 to a 1 because it was told so. So to put it mathematically, what does that look like? So what we're gonna do is define a cost function. Okay, it's also called a loss function. All right, come here. What we're gonna do is backprop. All right, what we're gonna do is define a cost function. For now, I'm taking the mean squared error. Okay, there are a lot of cost functions. Okay, cross entropy loss, there are a lot, but I'm just gonna, for now, I'm just taking this. Even the sigmoid function, the activation function I was talking about, there are a lot of functions. Okay, there is rel-u, there is tanh, and there are like a lot. Okay, there is leaky rel-u. So for now, we took sigmoid for that, and I'm gonna talk about the cost function, the mean squared error. So what that is nothing but output minus the actual value squared. Okay, why are we doing this? Okay, let's say you can tell the baby that no, that's not a 1, it's a 5, right? But how do you tell the computer that, especially when the output looks like this, right? 0 1 2 3 4 9. That looks like 0 0.1 0 0.3 0 0.7. How do you do that? So what we're gonna do is we already have the label. So well, we already have the actual label, so what we know what it should be, right? So that is y holds if, well, let's say we the x, what we fed in was an image of a 6, the y will hold just a value, just a number 6. Okay, so first we need to turn this y into the outputs form. Okay, this is called one hot encode. It's nothing but like the y will become a matrix. It'll have 0 1 2 3 4 5, will become like the output 6 7 8 9, and everything will be 0 except where it's 6, right? The 6 part will be a 1 and everything else will be a 0. So we're gonna turn our y into this. This is called one hot encoding y, and then we're gonna take this. Now we're gonna take the difference of o minus y, and we're gonna square it so we get a positive value. Why are we doing this, and why are we calling it a cost function or a loss function? Okay, now the assumption here is the whole network. This whole network is a cost function. Okay, I can't seem to find the image, but let's see. Let me just draw like the x, a1, a2, o. Okay, let's say this is our network. Now that cost function is a function. Okay, that cost function is the equation of the whole network. Okay, like how a1 is the equation of this layer, a2 is the equation of this layer, o is the equation of this layer, right? C is the equation of everything in here. I want you to think of it like that. It's an equation of everything. And well, and it's pretty simple, isn't it? Like we have defined it, C as o minus y whole square. But how is it an equation of everything? Well, it has o in it. Okay, so we have this one. Okay, we can just take green and tick this. All right, we go back to the o equation. O equation has a2 in it, so that means the o also, we also have a2 now in C. So we go back to a2, it has a1. So a1 right here. So the cost function also has a1. All right, check. And we go back to a1, it has x. and the cost function also has x. So it's a function that has all the equations in it. So it's the cost function is the function of the whole network. So now what we're trying to do is trying to minimize the cost function. Why are we trying to minimize it? Okay, let's just look at the cost function. It's something square, right? Let's take it as y square. Now, let me get a new variable. Let's take it as a minus b whole square. Okay, this is the equation. Z equals to a minus b whole square. Now, what is the least value that z can have? Think about that. What's the least value can z have? Well, since there's a square, the least value that z can have is a 0. Okay, well, how can we get a 0? Okay, a minus b whole square equals to 0. A equals to b. So if a equals to b, z is 0. Okay, so exactly using the same logic, we need to make this, the least value of the cost can be 0. Okay, and it only happens when o minus y equals to 0. That means o equals to y. What is o again? It's the output, isn't it? It's the output of the function of our neural network, right? What is y? Y is the actual label of the image that was fed in. It was the label, right? So what does that mean, that output is equal to y? What does this equation right here mean to you when you think about it? That means the output that we got from the neural network is exactly the same as the label of the image that we fed in. Okay? Isn't that what we were trying to do? Think about that now. Exactly, right? That's exactly what we're trying to do, isn't it? We're trying to get the output of the image to match exactly with the label. Let me write the equations again. So we're going to be writing these equations a lot repeatedly, so we do not forget. So let's write A1 equals to sigma of W1 transpose dot X plus B1. Okay, we can write this as another variable. We will just write it as Z1 equals to W1 T dot X plus B1. Okay, so what does that mean? That just means A1 equals to sigma of Z1. Okay, it looks cleaner. That's the only reason we're putting it in there. So the variables are less congested and it's easier for us to like interpret. Similarly, we're going to do the same things for A2. A2 is nothing but sigma. Well, we're going to use, in the coding part, we're going to use rel-u as well. So that's, I'm just putting it out there. That's fine. And plus B2. And we can write a sigma of Z2. And A3, there is no A3, there is just output equals to sigma of W3 transpose A2 plus B3 sigma of Z3. All right, now before I tell you how to reduce the cost function, I wanna talk about, well, we're gonna do some calculus right now. So imagine this is a function. How do you find the lowest point? Okay, calculus students will be like, well, we can just take the derivative of x with respect to y and grade it to 0 and we'll find this point. And yeah, that was pretty simple. But what if the equation is a little bit complex, okay? What if the equation's like that? How do you find it? So, well, there are a lot of local minimums, right? This. So the best part to find a local minima, and the best way to find a local minima is start at any old point, okay? Find the slope of that point. If the slope is positive, move to the left. But if the slope is negative, move to the right. Okay? Well, that is for a two-dimensional space with one variable. One variable, two-dimensional space, that's how we do it. All right, what about a three-dimensional problem? So, well, it's pretty simple. We're going to find something called a gradient. Gradient is nothing but It's a vector that shows you the, well, what is a vector? Vector holds two things, magnitude and direction, okay? So when you take a gradient of function, okay, this function is called, let's give it a name, z equals to something like 5 by 3x squared plus 3 by 2, 3 by y squared. Okay, this is probably not right or wrong, not right, but yeah. So let's say we have this point on the z function, okay? If we take the partial derivative of z, that is dz by dx, okay, and put it, and let's say we got a for that, and dz by dy, let's say we got b for that, okay? So we get a and b for this point right here, okay? And we got a and b, right? We put it in a vector. That vector shows us the direction of the greatest, steepest ascent, okay? That vector gives us a little bit of magnitude and shows us the direction of the uphill. But what we're trying to do is find the direction of the downhill because we want to reduce our cost function, right? We want to make the cost function 0, okay? That is like right here, but, well, we cannot go there because we didn't start there. If we're lucky, we might get there. So we're just right now we're just trying to minimize it. We cannot find the 0, okay? It's not realistic. So we're just gonna find some local minima where we can be happy with the cost function, okay? So that's what we're doing. So when we find the gradient, this is called gradient when we do the partial derivation and put it in a vector form. When we find this gives us a vector that shows the steepest ascent. Now we want to, that increases. If we go there, we're right here right now, okay? We're at that dot, okay? And we got AB, okay? AB is that point right there. Let's say we had m comma n, okay? That's what we had. We took the derivative and we substituted m comma n. And here as well, m comma n. And we got a comma b. A comma b is this, okay? That point, a comma b. So this is the vector. So it's telling us to move up, steepest ascent, okay? But how do you move up? You're just gonna add that point to that. It's no big deal, okay? But what we wanna do is we wanna go down, okay? So what we're gonna do is we're gonna take the negative of the gradient. So that will give us, instead of this point, it's going to give us some point right here, which is going to be opposite. So it will give us the gradient descent, okay? And then we're going to multiply that with a scalar value, a scalar called learning rate, okay? To like get to increase the magnitude of our gradient descent so we reach the local minima faster. That's the whole point of learning rate. But there's a problem. If you, we have the flexibility to choose the learning rate, but think about it like this, okay? You have this function, okay? You're right here. You're, ooh, how did you do that? Okay. You're right here, this point. Okay, and let's say you took the gradient of the function and the gradient was here. You took the, let's say the gradient was the triangle. Okay, it's usually the gradient is represented by the upside down triangle. Okay, it's telling us to go up. We take the negative of the gradient. It's telling us to go down. Okay, now let's say alpha is our learning rate. Okay, we multiply that to this, so it's gonna increase our increase the magnitude of that vector so we reach the local minima faster. But the problem here is if you take the alpha very small, okay, let me write alpha very small, it's gonna take you from here and your alpha is very low. You're just gonna take small steps every iteration. It's gonna take you forever to reach this point. But if you take alpha equals to very big, then you're just gonna overshoot it, Okay, you're gonna be here the next time, and then you find the negative gradient again, and then you're gonna be here. Then you're gonna just overshoot the local minima. So you need to be very careful while picking the learning rate. Okay, so yeah, so that's how it's done in a 3-dimensional space. Okay, 3-dimensional space, 2 variables. All right, okay, coming back to our question, how many variables do we have? Well, we have close to 13,000. Well, we have exactly 13,002 variables. What does that mean? That means the problem, the equation, the cost function is in a 13,000 dimensional space. Okay, we cannot fathom, we cannot picture it, but the laws of mathematics stay the same. Okay, plus is a plus, minus is a minus, derivative is a derivative, so they stay the same. Okay, so I want you to picture the 2D graph that we were talking about, and we're gonna work with that in this 13,000 dimensional space. All right, stay tuned. Cost function. So the cost function equals to output minus label whole square. Derivative of cost function is nothing but 2 of O minus y. Okay. We're gonna do derivative of cost function with respect to W3, and we're gonna call it W3. That's the mathematical notation. We're gonna call this as dw, dw3, the variable, and that will be 2 into O minus y into, we're gonna expand O to sigma of z3 whole. We need to still derive this part, so it's gonna be d by dw3, right? So that will be O minus y into sigma dash of z3 into derivative of z3. So what is the derivative of z3? We're going to expand that, and we're going to get w3 a2 plus b1 b3. All right, and this will be 0 because it does not have the w3 variable, and the derivation of w3 will be 1, and it's just going to give us sigma 3 z3 into a2. So here I want to highlight one very important part. Starting from here, here I want you to do this. This is element-wise multiplication. It's not dot product right here. Okay, I want you to keep that in mind. So 2 minus O, output minus this will have 10,1 dimension into element-wise multiplication. Even Z3 will have the same dimensions, okay? 10,1, okay? So they together will produce, then we have to dot it. Let's write dot. So we have to dot it with A2. So they'll produce this element-wise multiplication. Then we're going to do dot with that. So it's going to be 16,1. And we already know the W3, we already know the shape of this. It will be the same shape as the weight of W3, which is nothing but 16,10. So we're just gonna take the transpose of this. Let's write this part. You see this? Let's put this in one variable, and let's call that variable dz3. Okay, so dz3.a2 is currently what we have. We're gonna turn this into a2 dot, this is a dot product dot dz3 transpose. Okay, let me just write transpose like this, it's fine, dot t. Okay, we're gonna transpose that, so it's gonna become 1 comma 10, and this will be 16 comma 1, so the resulting will be a 16 comma 10 matrix. So we have found delta 3, so this was dw3. So how we update the weights is, I'll get to that when I get to that, but how we update the weights is like the current weight w3 equals w3 minus a learning rate, okay, multiplied by the gradient w3. Okay, that will take the weight closer to the gradient descent, the local minima. It will take the weights, it'll take w3 weights closer to the local minima. Now that we have this equation, I'm gonna highlight it with green. Okay, so this is the final equation, and a dz3 is nothing. Wait, sorry, dz3 is the red box right there, so I'm gonna highlight that with green as well. So we need to be careful of these equations. Okay, that was just w3 though. What about, how will we find, similarly for delta, similarly for delta b3, okay, the gradient the gradient for bias b3, we're gonna do is the same thing. We're just gonna take the derivation of the cost function with respect to b3 though. So it will be 2 of, let's take white, 2 of o minus y into sigma of z3 into, here we're gonna expand it, and we're gonna cancel out. Okay, we need to take the derivative of this. I'm just expanding z3 here. Okay, z3 is nothing but w3 a2 plus b3. This term right here, this term does not have b3, okay, so this will be 0, and it has b3, so derivative of b3 with respect to b3 will become 1, so it's just a multiple of 1. So this is nothing but the green box right here that we described as dz3, okay? dz3 is nothing but this. So we can write delta b3 as dz3, which is nothing but derivative of cost function with respect to b3. Okay, so let's derive the gradient of w2. Okay, so we're gonna call the variable, this is called a variable dw2, okay, and that's nothing but cost of a derivative of cost function with respect to w2. All right, so it'll be 2 of o minus y. Okay, now we have to do derivative of o with respect to w2, which is gonna be sigma of z3, because that's what o is. And now we have to take the derivative of z3, which will be, let's do this. Let me write it out because we're gonna have to cancel some terms here. We're gonna go w2 on the bottom. That's what we're doing with respect to. So it will be w3 a2 plus b3. We can go, this term does not have w2 term, so those will be 0. The w2 term is in a2, okay? So we'll treat the w3 as a multiple. We'll take that out. So minus y z3, I'm just writing the thing, and I can write w3, and a2 can be written as, we have a equation that is sigma of z2, right? So a2 can be written as sigma of z2, and we can take the derivative of that, of u2. Okay, and zoom out a little bit, 2 of o minus y, sigma dash of z3, w3, sigma dash of z2. Now derivative of z2, expanding z2. Derivative of z2 with respect to w2, we have w2 a1 plus b2. Okay, so this will be 0 because there is no w2 term. We found the w2 term with respect. If we take the derivation, it will become 1, and we'll be left with a1. So let's write this out. O minus y, z dash of 3, w3, z2, and a1. All right, congratulations. We have found the gradient descent of W2. Okay, we're gonna have to simplify this first. We already know this part. We have already assigned a variable, so I'm just gonna call in that variable, and the variable was, we're just gonna look for it again. It's right here. We called it dz3, right? See, 2 of o minus y, it's right here. 2 of o minus y into element-wise multiplication with this, and that gave us dz3, right? Okay. What's dz3 is nothing but 10 comma 1. Okay, right? It's crazy. Okay, dz3 is nothing but 10 comma 1. We're gonna write out the equations. Let's see, w3. Well, w3 has 16 comma 10, right? W3 dimensions. Now we're gonna choose sigma dash of z2. Remember, this term needs to be element-wise multiplied. Element-wise multiplied. Okay, be very careful. So that term needs to be element-wise multiplied. So we're gonna do that. Now, what is the dimension for z2? It's going to be same as a2, which is 16 comma 1, and a1 dimensions we already know, 16 comma 1. All right, so what we're going to do is we're going to transpose the weight. Okay, so we're going to transpose the weight, so we're going to have to transpose the dz3 again to multiply with w3. Wait, isn't that what we did? Oh, never mind. There was no... Okay. So we're going to have to multiply dz3 with... So we'll write it out like this. Okay. Dot with dz3 dot transpose. Okay, so it will be, so here we have 16x 10, and here we have 1. Oh wait, we don't have to transpose it. Never mind. What am I doing? There is no need to transpose here. We can just write it as 10x1. So this will give us 16x1, okay? Now we need to do element-wise multiplication. After we do the dot, we first do the dot, and then we do the element-wise multiplication with sigma dash of z2 right here, 16 comma 1. So the resulting will also be a 16 comma 1, okay? So we're gonna take that, and let's give this whole thing, let me use blue, let's call this whole thing dz, okay? I'll write it right here. let me bring in the A1 term as well, so we don't miss it. But yeah, I'm gonna create another variable called dz2. Okay, dz2 is nothing but w3 dot dz3 and star. I'm just gonna put a star for element-wise multiplication, so I know while I'm coding. And we're gonna go call it sigma dash of z2. Okay, that's what dz2 is. So dz2, I'm gonna write it here, and the dimensions is 16x1 dot a1. I want to see what I did here. See, I transposed dz3, so that's what I'm gonna do here as well. Okay, I mean, we just have to match the dimensions of this to, this is delta w3 and w2, right? So we need to match the dimensions to w2's dimensions, which are 16x16. So that's what we need to do. But we can do it multiple ways here, but I'm gonna do it so that we have like you know, similarity in equations. So I'm gonna pull a1 here, a1 16,1, and I'm gonna do dz2 dot t, and will give us 1,16. And when we exit, we got 16,16. Okay, so this satisfies w2, and congratulations, we found w2. Similarly, if we do for delta of bias 2, right, we'll have the same equation, but instead of a1, we'll have 1. You know why? Because it's going to expand similarly, like exactly like this, exactly like how this expanded. So this is the total expansion, right here. You see this expansion? Let me highlight it for you guys. You see this expansion? It's going to be exactly like this, but here, instead of b2 being 0, this term will be 0, and the denominator will be b2, right? So we're looking for b2 term, and we find it here, not here. So this will be gone, and this will become 0, and this will become 1. So that term will become 1, and only this term is what b2 is. So that term is nothing but this term right here. And we can just write this down, dz2, okay? If you don't understand it, derive it yourself, and you'll be able to understand what I'm talking about, okay? And yeah, and there's one last one. You need to find w1 and b1, and we'll be all set, okay? So let's do derivation of cost function with respect to w1. Call it dw1. That's the variable name. And now we're gonna do, okay, what should be the dimensions of this? The dimensions of this will be 16, okay? It'll have the same dimensions as w1. And even this, the above part, this will have the same dimensions as 16,1, and even this will have 16,1. Okay? And okay, let's start deriving again from the top. D of output minus whole square by dw1. Okay? This is going to be the biggest one yet. Alright, let's go with 2oy. I'm going to go fast now, okay? Hopefully you guys are able to follow up. Now we're going to do sigma dash of z3. And we're going to do w3 and sigma dash of z2. I'm going to do w2. And let's see, what else will we have? w2, then we're expanding a1, so sigma dash of z1. Okay, z1 is what? X into w1. So here we'll have, instead of W1, we're doing derivation of W1, we'll have X, okay? So this is the big equation of W1. We're gonna do the thing where we put it into smaller terms. So we have this is nothing but dz3, and dz3 into, wait, what was that? dz3 dot w3 into this, right? w3 into this. So if we take these two terms down here, like down here, w3 sigma dash of z2, we can get a variable, okay? And that variable is nothing but dz2, right? dz2 dot, what is dz2? dz2 is 16 comma 1. That's the dimensions of dz2. So 16 comma 1 dot w2 sigma dash of z1 dot x. Okay, this again, I'm telling you guys, please keep this in mind. This needs to be element wise multiplied. Element-wise multiplication needs to be applied to this, okay? Remember, if you do dot product, you're not gonna be able to find the gradient descent. I want you to be very careful here. All right, what is W2? Weights of W2 are 16 comma 16. And what about a Z1? How does Z1 look? Same as A1, so 16 comma 1. Well, how does X look? X is our input, and we're gonna put 1 because we have derived everything using like just one example, okay? Usually it will be N, like number of samples. That won't be 1. This part, it won't be 1. It will be N. It'll be number of images fed to the network, okay? I've taken as 1, but it will usually be N, and that would change different things, but we can take 1. It's fine. It'll still give us the same calculation. Instead of 1, it'll be an N, so other terms will have N in them, and we'll be able to do the dot product. Okay, for now, let's do this. We'll do, okay, did we take, I want to look back for a second so I see what I did. So I took, okay, W3 dot, so I'm going to take W2 here now. W2 dot DZ2, okay? So W2 is 16 comma 16, DZ2 is 16 comma 1, and sigma dash of Z1 and X, right? So I'm going to do dot product of these two, okay? Dot product, so that will give me that'll give me 16 comma 1. Then I'm gonna do element-wise multiple. First I'm gonna dot this, okay? Whatever I get, this matrix I'm gonna do element-wise multiplication with Z1, and I'm gonna call that Z1 as DZ1, okay? That whole thing. Dot X and dot X. I'm simplifying the equation here. Just so you know, you can write this equation out. You see this whole big equation? Let me yellow, okay? Okay, you see this equation? You can just write this equation out like in while you're coding, but I'm making it simpler so they're like the equation doesn't look scary, okay? I'm just making it so that we have like smaller variables which are holding more stuff, okay? So DZ1 is this and dot X, okay? So this is 16 comma 1 and X is 784 comma 1. So, and we're doing delta W1, which is nothing but 784 comma 16, okay? So what we need to do here is go X dot DZ1 dot transpose. So that will give us 784 comma 1 here and 1 comma 16 here, which will cancel out ones, and the resulting will be a 784 comma 16 vector, which is same as the W1 matrix dimensions. Okay. And similarly, obviously, if you've been following through till now, delta of B1 will be the whole thing. It will just be DZ1, okay? That was 16 comma 1. And we know that DZ1's dimensions are also 16 comma 1. All right, we have successfully derived everything. We have the gradients of the weights. Now we just need to multiply these with a learning rate and subtract it from the weights, original weights. Okay, what we're gonna do is we're gonna do W1 equals to W1 minus dW1 into learning rate. Okay, and similarly for B1 we're gonna do B1 minus D B1. This is dB1, by the way. Okay, those are just variable. The triangles is just D, okay? Just think of it like that. The triangle is D. And into learning rate, the same thing. So W2 will be the similar thing. We've derived everything. What I'm going to do is I'm going to write it in a block so I can just I can just look at it while I'm coding, so it'll be easier for me to do.